Welcome back. How are you? Hope you are doing good. Okay, in the last session, we covered the principle of oscillations, right? Then I explained what is gain margin. Now, let me explain what is gain margin, phase margin with respect to Bode plot. Then we can directly go to the circuits, oscillator circuits. Okay, what is the topic? Topic is sinusoidal oscillators. This is the topic. Okay, now for example, let me take, right, what is our system? If you take, we are analyzing for the closed loop system having G of S and representing with unity gain feedback, and this is your output V naught and this is your input Vi. For this system we are trying to analyze system stability, but we are considering G of S, right, and calculating with respect to G of S what is gain margin and what is phase margin. Now example 1, let us say G of S is having something, right? Then if you take Bode plot, this is what is example 1, right? If you take Bode plot, which is nothing but polar plot, but I'm just taking Bode plot. Now if you take Bode plot, this is what is gain margin and this is the frequency, let us say, and this is what is phase margin. I'm trying to explain, just listen. Now always the reference is 0 dB. 0 dB is nothing but what? Gain 1. 1 is always reference, and what is our reference? Minus 180 or plus 180. This is what is our reference. I told you what is the reason, because our reference is always minus 1, always minus 1. 1 is indicating the magnitude, minus is indicating 180 degrees. If this is giving 180 degrees, right, the total loop phase shift, that is what is 0 degrees. At what frequency the total loop phase shift is 0 degrees or multiple of 2 pi, or at what frequency G of S is contributing 180 degrees in this representation, then remember that time the gain, the loop gain is basically your G of S gain. The gain of your G of S should be less than 1. Then only you will get stable output. If G of S gain or loop gain is greater than 1, then system is not stable. Is equal to 1, marginally stable. That is what I told, right? Now if I say this is what is your gain plot, let us say this is what your gain plot, okay, and if you ask me the phase shift, right, maybe it is what is having some phase shift, let us say this is what is the phase shift, okay. Now tell me whether this system is stable or not, right? Directly we can say, very simple, this is what is your gain, this is what is your mod G of S, okay, and this is what is angle of G of S, angle of G of S. Therefore now tell me, first of all, to calculate gain margin, what we need to do? The frequency at which the phase shift is 180 degrees. Therefore what is the frequency? Can I say this is the frequency? Yes, this is the frequency. The frequency at which, this is what is called gain crossover frequency. Therefore because I am representing with F, anything is fine. Therefore this is what is gain crossover frequency, omega or F, anything is fine. Therefore this is what is, sorry, phase crossover frequency, omega PC, right? Therefore tell me exactly at what frequency the phase shift is 180 degrees from your open loop, from your G of S. Therefore now this is giving 180 degrees phase shift at this frequency. Now at this frequency you see what is the gain. At this frequency what is the gain by your G of S. Therefore that is nothing but your loop gain, which is nothing but A beta, example what I gave before. But here this is G of S, which is loop gain in this case, because this is what is having unity gain feedback. Now tell me, is gain greater than 1? When I say 0 dB, this is nothing but 1. Therefore greater than 1, yes, this is what is greater than 1. let us say this value is some 20 dB. Let us say it is having some 20 dB. Now if you ask me what is gain margin, this is what is gain margin. It should be negative actually. Sorry, it should be less than 1. Then negative. What it may be, this is greater than 1, which is 20 dB. Then if you ask me what is gain margin, now gain margin with respect to 0 dB. Actually, gain margin is defined as gain margin is equal to 0 dB minus gain. 0 dB minus gain, which is 20 dB, which is minus 20 dB. Therefore, what is gain margin? Gain margin is negative. See, don't remember how to say. You may confuse 0 minus 20 dB or 20 dB minus 0. You may say this is gain margin, which is 20 dB, therefore positive. No, very simple. That's what I'm saying. The frequency at which phase shift is 180 degrees. The frequency at which the phase shift is 180 degrees. Exactly at the frequency, the gain should be, mod A beta should be less than 1. Mod A beta should be less than 1, but it is more than 1. Therefore, gain margin is negative. You can remember in that way. Because gain margin is negative for unstable systems and gain margin is positive for stable systems. Now let me explain phase margin. Now I can explain phase margin. Now what is phase margin? This is with respect to what? This is with respect to 180 degrees. Now with respect to 0 dB or 1, the frequency at which the gain is equal to 1, that time it should be what? Above minus 180. If it is above minus 180, then above minus 180 means it is in between 0 to minus 180. If it is in between 0 to minus 180, it is like effectively less than 2 poles. Then overall the system is stable. If it is more than 180, it is crossing 1, then indirectly it is unstable system. What it may be. Therefore, let us say this value, this is minus 220 degrees. Then if you ask me what is phase margin, always reference is what? Reference is minus 180. Now if you ask me what is phase margin, your phase margin is defined as whatever phase shift. Let us say this is what is your phase shift you got. This is nothing but your phase shift at this is nothing but gain crossover frequency omega GC at gain crossover frequency. Okay. Therefore now tell me, this is what is that gain crossover frequency. Therefore what is phase margin? Phase margin is defined as 180 plus 5. Therefore what is 5? Minus 220. Therefore 180 minus 220, which is equal to minus 40 degrees. Therefore this is negative. Gain margin is negative, phase margin is negative, system is unstable. System is unstable. System is unstable. Our system is not stable. Why? Same thing. Therefore, actually one point is enough, but we are explaining in a different way. One point is enough. Okay, that is nothing but gain margin. So remember, either gain margin is positive or gain margin positive, phase margin positive. Gain margin negative, phase margin negative. There is no combination of gain margin positive, phase margin negative. That combination is not there. Actually, one point is enough. Either you can define gain margin, or this is sufficient to speak about system stability. Either gain margin or phase margin. Any one of these two parameters are enough to speak about system stability. Right? Both are not required. But in a different way, we are trying to measure what is gain margin, what is phase margin. Okay? That is fine. Therefore, system is not stable. Now, I can give you another example. Therefore, example 2. Example 2. Right? Now, again, if I give you a Bode plot, this is what is our G of S, mod G of S. Right? We always take gain of loop gain, phase shift of your G of S. Now, this is what is our frequency again. Now, let us say this is what your 0 dB, which is your reference, and this is what is minus 180. Okay. Now, if you see here, let us say this is what is your gain. Okay. And this is what is your phase shift. Right? Now, let's see whether system is stable or not. What it may be? You know Bode plot. If you know Bode plot, simply I can say whether system is stable or not, and if system is stable, how much margin you have with respect to gain and how much margin you have with respect to phase shift. Margin with respect to 180 degrees and gain margin is with respect to 0 dB or 1. Therefore now tell me, right, just these two are enough for us, that's it. Therefore now tell me the frequency at which your gain is equal to, or phase shift is equal to 180 degrees. This is what is phase crossover frequency omega PC, right? Then if you calculate how many poles it has, doesn't matter. How many zeros, whatever it may be, if you know gain plot, phase plot, I can speak about gain margin, phase margin. How many poles are there, how many zeros are there, doesn't matter for us. Ultimately, the system which is having poles and zeros will be reflected into gain and phase, both. Therefore, now let's see. The frequency at which the phase shift is 180 degrees, the frequency at which the phase shift is 180 degrees, exactly at that frequency you need to find the gain. If the gain of this, that is nothing but A beta, that is what is your A beta, right? Therefore, if that A beta less than 1, system is stable. Greater than 1, system is unstable. Is equal to 1, system is marginally stable. Okay, what it may be. Therefore, now if you see exactly the plot, right? Now maybe if you ask me this value, right? This is with respect to 0 dB. Let us say this is what is some minus 60 dB. Just I am giving one example. Therefore, this is what is our gain margin with respect to 0 dB. Therefore, what is gain margin? Gain margin is positive. The absolute gain whatever you are getting at phase crossover frequency, right? Minus of that is nothing but your gain margin. Remember. Or simple, don't remember whether it is minus of minus, I told you already. At frequency, at phase crossover frequency, gain should be less than 1. This is our reference, it should be less than 1 always. Then only system is stable. Right? Here, at phase crossover frequency, the gain is greater than 1. System is not stable. Okay? Now let's see. Therefore, what is gain margin? This is what your gain margin. Therefore, gain margin is equal to 0 dB is reference minus 60 dB. Therefore, this is nothing but 60 dB is the gain margin. Okay, that is positive. Therefore, this is what is positive. Gain margin here is positive. Here also it is positive. With a positive in the sense positive and negative with respect to dB, not with respect to ratio. Okay. This is negative. This is negative. Okay. This is positive. Now let's see. This is what is our phase crossover frequency. What is gain crossover frequency? The frequency at which the gain is equal to 1. Exactly that point. What is the phase shift? It should be in between 0 to 180. Therefore, this is what it is. Let us say this is what is some minus 100 degrees. Let us say. Right? Then, what is our phase margin? What is our phase margin? That is with respect to 180 degrees. Okay? Here, this is nothing but angle of G of S. Therefore, what is phase margin? Your phase margin is defined as phase margin is equal to 180 plus 5. 180 plus 5 is nothing but minus 100. Therefore, this is nothing but 80 degrees. Is it positive? Yes, this is positive. Phase margin is positive. Here, phase margin is negative. Right? Therefore, tell me, system is stable. System is stable. For example, gain crossover frequency is equal to phase crossover frequency. Then that is nothing but marginally stable system. Right? Gain crossover frequency is equal to phase crossover frequency. The frequency at which gain is equal to 1, the frequency at which phase shift is equal to 180 degrees. That is nothing but marginally stable system. That is nothing but principle of oscillations. The system which has gain margin 0, phase margin 0, that will give you oscillations. That will give you sustained oscillations. But the frequency at which gain crossover frequency is equal to phase crossover frequency, that is nothing but resonant frequency or frequency of oscillations. Okay? That's fine. You take it. This is with respect to Bode plot. This is what normally people use in industry also. If you want to find stability of a loop, whatever loop, okay, then people use Bode plot. Bode plot in the sense gain response and phase response with respect to frequency of your input signal of a closed loop system, considering unity gain feedback. Okay. We have only three combinations. Remember, gain margin, phase margin positive, stable system, gain margin, phase margin negative, unstable system, gain margin, phase margin 0, marginally stable system. That's it. We don't have any cross combinations where gain margin 0, phase margin positive. No, we don't have those combinations. Okay. Either both are positive, both are negative, or both are 0. I'll give you 1 minute time. Try to plot in the time. Hope this is done. If this is over, then I'll give you summary. Okay, now summary. Therefore, what is summary? Number 1, gain margin greater than 0 and phase margin greater than 0. This is nothing but stable system. Number 2, gain margin less than 0, phase margin less than 0, anything, okay, then unstable system. Now case 3, gain margin 0, then surely phase margin is also 0. This is what is marginally stable system. Marginally stable system. But this is what is going to give you oscillations. This is what is going to give you oscillations. Sustained oscillations. That is what we are going to get. Okay? Take it. This is the summary. You can check only gain margin. Positive, negative, 0. Then other thing is also following. The phase margin is also following the same as gain margin. Now we can go to circuits part. There are 4 types of circuits which generate sinusoidal oscillations. Then we can see the figure of merit of each oscillator. Then finally we will stick to the oscillator circuit. Okay, that part I'll explain. That okay. Now let's see. The first circuit. The circuit name is RC phase shift oscillator. RC phase shift oscillator. Okay. Now just listen, don't write anything. Now if you take an amplifier, let us say this is what your amplifier, I'm just representing like this. This is what your amplifier A, which we are going to get using Opamp. Okay, that's why Opamp applications, I'm just taking it as Opamp applications. Then this is what is giving it to some beta network, right? You can write in any way. Let us say this is what is given to a beta network. Then output of beta network is given to input to your open loop amplifier. There is no external input. There is no external input. But if you observe clearly, according to Barkhausen criteria or according to the summary from Bode plot, we want gain margin is equal to 0, phase margin is equal to 0. Or if I satisfy or if I speak about the principle of oscillations, which are nothing but which is Barkhausen criteria. Now tell me, the total loop phase shift must be equal to 0 degrees to get oscillations. Okay, the total loop phase shift must be equal to 0 degrees to get oscillations. And the second point, the total loop gain must be equal to unity. The total loop gain must be equal to unity. Okay, therefore I told you out of those 2 points, the primary point is the total loop phase shift must be equal to 0 degrees. Okay, now let us say always out of these 2, always the primary circuit is nothing but beta network, because this is nothing but your passive network we should know how much is the phase shift which you are getting from your beta network. Let us say this is giving 0 degrees, then it has to give 0 degrees. If this is giving 180 degrees, it has to give 180 degrees. If this is giving 120 degrees, it has to give 240 degrees. Whatever may be the total loop phase shift must be equal to 0 degrees. Then only we will get oscillations. Okay. Now, one more point. Let us say, but always we deal with either 0 degrees or 180 degrees. The frequency at which total loop phase shift is equal to 0 degrees, that is what is your frequency of oscillation. Let us say your beta network is giving 180 degrees phase shift, but that will not give you 180 degrees phase shift for all the frequency components, right? It will give you 180 degrees phase shift only for a given frequency, right? That frequency will be the frequency of oscillations, provided this is also giving 180 degrees phase shift at that frequency. Then 180 total will be 0 degrees or 360, then you will get oscillations, right? Now you may ask, at a given frequency, yes, this is giving 180, therefore this is giving 180, total loop phase shift is 360, yes, fine. But let us say other frequency, this is not 180, right? Let us say this is 180, this is 170, this is 180, that will be died out. That frequency component will be died out. That will not have regenerative feedback, or that will not have positive feedback. That is not having positive feedback. We want positive feedback to restore the signal. Positive feedback is the one which is what is, if something is decreasing, right? Sorry, if something is lost, then open loop amplifier is the one which is what is going to boost, such that it is going to add the extra energy, therefore it is going to regenerate. That is what is called regenerative feedback. Okay, when it's a regenerative feedback or a positive feedback, you can get sustained oscillations. That is what is your loop gain. But to get positive feedback, the total loop phase shift must be equal to 0 degrees. Then how much is the loss by beta network and how much is the gain by your open loop network? That is what is nothing but your A beta. That A beta should be equal to 1. Then whatever loss you have from beta network, the same amount of energy will be given by your open loop amplifier. Therefore, you will get sustained oscillations. That is what is A beta is equal to 1. I hope this is clear. Now, let us start with beta network. If you start with beta network, therefore, if you take beta network, now, that too, if you see, the heading is nothing but RC phase shift. Therefore, if you take RC phase shift circuit, let us say this is R and this is C. Now, let's see how much is the phase shift you get. Okay. Then, let us say this is what your V0 and this is what your Vi. Then tell me what is the transfer function. Therefore, if you take transfer function, H of S is equal to R divided by R plus 1 by SC, which we have seen already. This is nothing but your high pass filter, okay, which has 1 0 and then 1 pole. Therefore, what is this? This is what is SCR divided by 1 plus SCR. Now I am looking for what? I am looking for phase shift by your single RC network. Okay. Then tell me what is the phase shift. Then H of j omega. H of j omega is equal to j omega RC divided by 1 plus j omega RC. Right? Therefore, then what is your phase shift? Angle of H of j omega, right? That is nothing but basically angle of H of j omega is equal to 90 degrees minus tan inverse omega RC. Let's see what is the maximum and minimum phase shift that you can get using single RC network, right? Therefore, let us say when omega is equal to 0, when omega is equal to 0, when omega is equal to 0, tell me what is the phase shift, what you can get when omega is equal to 0, tan inverse 0, 0, therefore phase shift is 90 degrees. When omega is infinity, when omega is infinity, highest frequency, tan inverse infinity 90 degrees, 90 minus 90, therefore 0. Therefore, tell me how much you can get. The maximum and the minimum phase shift that you can get using single RC network is 0 and 90, 90 and 0. Therefore, you can get in between 0 to 90. If you want to get non-zero frequency and non-infinity frequency, I want in between 0 to infinity, therefore I can get in between 0 to 90. Let us say maximum what you can get, maximum you can get 90 degrees at 0 frequency. Therefore, let us say this is what is giving 90 degrees. If this is what is giving 90 degrees, let us say you can use single RC network. If it is giving 90 degrees, then remaining what? We want to get total loop phase shift 0 degrees or multiple of 2 pi. If this is giving 90 degrees, I want 270 degrees from open loop amplifier. Do you have anything with 270 degrees? No. If you take Opamp, we have inverting amplifier, non-inverting amplifier. It is very easy to get 180 degrees phase shift for sinusoidal signals, and it is very easy to get 0 degrees phase shift. Therefore, it's difficult to get 270 degrees phase shift. Then what to do? It's better to adjust the phase shift from beta network. Let us say I'm trying to get 0 degrees or 180 degrees from beta network. If you're getting 0 degrees here, I'll get 0 degrees. If I get 180 degrees, I'll get 180 degrees. That is what is more than enough for me. Okay. Or the total loop phase shift must be equal to 0 degrees. That is also fine. Okay. Because I'm speaking with respect to practical scenario. Because you may say that it is giving 90 degrees, then get 270 degrees from open loop amplifier, then fine. But how to get or how to design the circuit which is what is giving 270 degrees phase shift? That is difficult. Therefore, we can get 180 degrees phase shift or 0 degrees phase shift. That is nothing but Opamp, inverting amplifier and non-inverting amplifier. I'm going to use those two to get 0 degrees and 180 degrees. Therefore, this is what is giving 90 degrees. Single RC network is not enough to get 0 degrees or 180 degrees. Let us target for 180 degrees. If I target for 180 degrees, right, what do you mean by 0 degrees? It's not 0 degrees, it is 360 degrees. Okay, I told you that point, because qualitatively if you ask me, 0 degrees is nothing but time domain 0, you are thinking in that way. No, it is 1 cycle delay, which is nothing but what? If you take a sine wave, 1 cycle delay is nothing but we think that the same sine wave is coming. Therefore, looks like with respect to sine wave, it is fine. But with respect to practical time, when you give input at time t is equal to 0, it will come after 1 cycle. Therefore, that is what is 360 degrees delay or 0 degrees delay. Right? That's fine. Now, can we consider two RC networks? Right? If you consider two RC networks, one RC network, let us say maximum it can give 90. If you take one more RC network, that is what is giving 90 and then 90. If you keep in cascade, then 90 degrees from first stage, 90 degrees from second stage, let us say, then total phase shift will be 180 degrees. Then it has to give 180 degrees. Then the total loop phase shift will be equal to 180 degrees. Right? Therefore, now let's say if you take two RC networks, this is what is single RC network. Now two RC networks, if you consider, right, then what you get? Therefore, this is what is one RC network, this is what is one RC network, and you are taking one more RC network. Then tell me, maximum it can give phase shift of 90 degrees. This is giving 90 degrees. This is giving 90 degrees. Right? Therefore, total beta network. Right? Now this is what is heading is beta network, but now this is one RC network. One RC network. That is what is the heading. Okay? Now two RC networks. Therefore, if you take two RC networks, we get 90 plus 90, 180. But at what frequency? We will get 90 plus 90 at frequency is equal to 0, at omega is equal to 0. What does it mean? At 0 frequency, it is giving 180 degrees phase shift, and this is also, let us say this is also giving 180 degrees phase shift at 0 degrees phase shift. Then the total loop phase shift is 0 degrees at 0 frequency. Means, what does it mean? The 0 frequency will be oscillating. What do you mean by 0 frequency? DC. Right? The DC will be oscillating. The DC will be oscillating continuously. What does it mean? We are getting DC. We are getting zero frequency signal. What do you mean by 0 frequency signal? DC only. Is it non-zero frequency which you are expecting? No. Therefore, let us go for 3 RC networks. If I go for 3 RC networks, then let us say each RC network is giving 60, 60, 60. Right? Therefore, if each RC network, let us say, if each RC network now let us say this is what is our output and this is what your VI. This is what is beta network. C, 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 and R, R, R. Let us say we have 3 stages. 1, 2, and then 3. Okay? We have 3 stages. Let us say this is what is giving 60 degrees. If this is giving 60 degrees, 60 degrees, and then 60 degrees. Therefore, now tell me, we have three stages. Therefore, can we get 60 degrees for non-zero frequency? Yes. Therefore, at a resonant frequency, this is what is at resonant frequency omega naught. That is what is your resonant frequency, which is not zero. Then your beta network is giving 180 degrees, and if your open loop amplifier is giving 180 degrees, total loop phase shift will be 0 degrees. At what frequency? At omega naught. Therefore, who is dictating the resonant frequency? Beta network is the one which is what is dictating the resonant frequency. Provided at that resonant frequency, I am expecting the phase shift by your open loop amplifier 180 degrees. Therefore, it will have bandwidth till that resonant frequency. Bandwidth till that that resonant frequency, and it has to provide 180 degrees phase shift. Once you get total loop phase shift is 0 degrees, and at what frequency the total loop phase shift is 0 degrees, that is what is your resonant frequency, and you will get oscillations exactly that frequency. That is what is first point. Then after getting the resonant frequency, then we need to get the second point. We should get sustained oscillations, not overdamped oscillations, not underdamped oscillations. We want sustained oscillations. Further, the total loop gain must be equal to unity. That part we will see later. Can we go for 4 RC networks? Can we go for 4 RC networks? Yes, we can go for 4 RC networks. Then each RC network will give 45, 45, 45, 45. Then you will get total 180 degrees. At what frequency you get 45 degrees from single RC network, right? Then that will be your resonant frequency. Can I take 5 RC networks? Each should give what? 180 by 5. We should get 36 degrees. Yes. 6 RC networks? Yes. 7 RC networks? Yes. You can have many number of resistor capacitor networks such that you will get total phase shift by beta network 180 degrees. At what frequency you are getting 180 degrees phase shift by beta network? That is what is your resonant frequency. Provided at that frequency it has to give 180 degrees phase shift, which we get normally, right? But the minimum number of resistor capacitor or the minimum number of RC networks to get phase shift 180 degrees is nothing but 3. 3 RC networks are required. Less than 3 RC networks we cannot get non-zero sinusoidal oscillations. Okay. Therefore, take it. Then let's calculate what is beta. Therefore, strictly speaking, if you take closed loop system, right, this is what is your output and this is what is your input for your beta network. But if you see with respect to feedback, this is the feedback quantity and this is what is your sampled quantity. With respect to amplifier, this is V0. That V0 is sampled and then fed back. And now this is what is your feedback quantity which you are feeding at the input. Okay, that's fine. Take it and let's calculate what is beta. Beta is nothing but the transfer function. Okay, this is what is acceptable. This is accepted. More than 3 RC networks we can take. Okay. Remember, either you can get 0 degrees phase shift or 180 degrees phase shift from beta network. Okay. In this example, we are trying to get 180 degrees phase shift from beta network. I'll give you 30 more seconds, then we will see, right? Let's see what is beta. Beta is nothing but V naught by Vi. Done? Okay. Therefore, let's calculate what is beta. What is beta? Therefore, here beta network is nothing but in this V naught by Vi. Therefore, how will you get V naught by Vi? Let me ask you a question, right, which is valid. Tell me, according to control systems, right, you know the transfer function of single RC network. If you know the transfer function of single RC network, which is nothing but SCR by 1 plus SCR. Now the same thing is cascaded. If the same thing is cascaded, if G1 of S, G2 of S, G3 of S in series or in cascade, then what is your effective transfer function? G1 of S into G2 of S into G3 of S. Am I correct? Yes. Then if you consider that, we know the single RC network transfer function, that is SCR by 1 plus SCR, then I want to know the total transfer function between V naught by Vi, then can I say SCR by 1 plus SCR whole cube, because all are similar. Then SCR divided by 1 plus SCR whole cube, right? If you say this is nothing but, if you say SCR divided by 1 plus SCR whole cube using control systems concept. According to control systems, if all the systems are in series or cascade, we can take G1 into G2 into G3. Okay? But that is what I have taken, but all are same. Therefore, G1, G2, G3, therefore whole cube, that is what is G1 is equal to, G into G into G, G cube, therefore SCR by 1 plus SCR whole cube. Then if you solve whatever equation you get, but now I can solve the same thing using nodal analysis. What is nodal analysis? This is what your V naught and this is what your Vi. According to nodal analysis, what you get? You can take it as V1, V2, then that's it. Then apply nodal analysis, you will get 3 equations. If you solve those 3 equations, finally you will get the relation between V naught and the Vi. If you solve using nodal analysis, then your beta will be, which is nothing but V naught by Vi, that will be equal to 1 minus 5 alpha square minus j into 6 alpha minus alpha cube. This is what you get, where alpha is equal to 1 by omega RC. This is what is your beta. Remember, if you solve using this, considering all 3 or all 4, all 3 are in cascade, then remember, this is wrong. If you solve using this and then if you get, and if you solve using nodal analysis, both should be same. But you will not get correct one, or that is the correct one which I can say using nodal analysis, but I am sure this is not correct. Now the question is why it is not correct. Then the control systems techniques whatever we studied, are they not correct? Or something is there, therefore we are not considering that. If something is true, then only all are true. Think about it. I will discuss about this in the next session, right? But remember, we should not take like this, because few of you may have the doubt. Therefore, because we know the transfer function of single RC networks, then if I have, they are in cascade, why don't you take SCR by 1 plus SCR whole cube? then you will get it. No, we cannot use it. I'll tell you the reason, but think about it, why it is not correct and why we cannot use. Then go back to control systems and then refer and then see why it is not correct. Right? If it is correct, for what condition it is correct? You think about it. But if I apply nodal analysis, I'm not showing how to get it, but if I apply nodal analysis, V1, V2, then apply nodal equations, then you'll get the relation between V0 and Vi that is straightforward, which is nothing but 1 by 1 minus 5 alpha square minus j into 6 alpha minus alpha cube. This is what is your beta network having j term, and therefore it is having some phase shift for different frequencies. But we are looking for at what frequency the total beta network is going to give you 180 degrees phase shift. That will be your resonant frequency, which I'm going to substitute. Okay. Take it, then we will see the Bar-Khausen criteria. Now we got to know what is beta. Now from that, let's calculate what is resonant frequency, and let's calculate what is your open loop amplifier gain and the phase shift requirement from your open loop gain. With that, RC phase shift oscillator is over. Okay, time is almost done for this session. You take it, then we will continue in the next session. But think about it, then I will discuss this in the next session. Okay, thank you.